Okay, welcome to induction video number 3. We're going to start looking at the way induction affects circuit behavior a little bit in this one. So I have a coil of wire already illustrated here, and a long coil of wire is also called a solenoid. That's something that I talked about last time. And in this particular diagram, based on the way the wire is wrapped, it's kind of drawn, it's supposed to be like a little bit 3D-ish. So like as the current goes down, it is in the front part of the coil, and then on its way back up, it's in the back, so it goes behind the other coils. But based upon that direction for the winding to go, if I send in current from the right, just realized that I didn't even indicate the current direction originally. So the current is coming in from the right, going to the left. I just said that backwards. It's going from the left, going to the right. But I do have the dots and X's indicated for the current direction as well. So like along the top part of the coil, the current is always coming out of the screen at you, and along the bottom part of the coil, current is always going into the screen away from you. And so if you do some right-hand rule stuff for that, you should find that the direction of the magnetic field inside the coil, inside the solenoid, has to be to the right, which is what I've indicated with my blue magnetic field vectors. So let's just assume that this has been on the steady current flowing for a very long time. If I then turn off the current, like I hit a power switch or I disconnect the battery or whatever, I want to go through a little bit of logic about what's going to happen with this particular part of the circuit. What's going to happen here in the solenoid. So the reason there's a magnetic field in the first place is because of the flow of current. So if I turn off the current, that means that the magnetic field should go away. So the first step of logic here is that the magnetic field is going to turn off. However, this magnetic field is passing through a whole bunch of coils of wire. And I know from previously that if the amount of flux through a coil of wire changes, that I should get these induction effects according to Faraday's law and Lenz's law. So while the current is on, there's flux pointing to the right that goes through the whole length of the solenoid. But when I turn off the current, and therefore turn off the magnetic field, I'm decreasing that flux. There was a flux to the right, and I'm trying to change the flux to be 0 instead. So there's going to be an induced EMF within the coil as a result of this change in flux, because the induced EMF through any coil is negative n d phi dt. So if I am making all of the flux disappear, there's definitely a d phi dt, and that means I'm going to get an EMF. And then I need to think about the direction for that EMF. The induced EMF is supposed to produce a magnetic field, an induced magnetic field, which works against whatever flux change was occurring in the first place. So if I'm trying to get rid of this flux to the right, that means I should make an induced EMF, which will cause an induced current to flow, which will make an induced magnetic field to replace the magnetic field that I'm losing. And in this particular case, I've already done the right-hand rule here, so I know that if I want a magnetic field that points to the right, I need a current that flows in the direction of the original current. And that goes back to this idea that the induction effects according to Lenz's law, the induction effects are always going to try to prevent whatever change is occurring. So if the change in the system here is that I have turned off the current, the induction is going to try to maintain that current. It's going to try to keep it going instead. So when I turn off the current, this chain of reasoning about all the induction is going to make it so that an induced current continues to flow through the loop, even though I have turned off the source. Now, it's not going to last forever. It's going to die out over time. But it's going to sort of slow down the process or smooth it out a little bit. And conversely, if instead of turning off the current, I tried to like boost it, if I wanted to make the current stronger, then I would get an induction effect again in that case, because if I increase the current, I'm going to make the magnetic field stronger, and that's a change in flux through the solenoid, and so there's going to be a Faraday and Lenz effect that produces flux going the other way, and that would require a current to flow the other way, or basically trying to weaken the current or prevent me from increasing it, or however you want to think about it. You'll occasionally see this phrase back EMF, and that just means an EMF that goes the other direction from the original EMF. So like presumably there's a battery or a generator or something that provides an EMF in a particular direction. And so if I try to increase the current, then the induced effect is a backwards EMF that tries to prevent me from increasing the current. You don't need to know this term. Like, I don't think it's going to show up on the AP exam or anything, but if you ever read people talking about electronics and electricity stuff, you might see the phrase back EMF. And it's an induction-related effect. So the point here is, I've got this solenoid, there's some current flowing through it, and if I do anything to the current, if I try to increase it or if I try to decrease it, there's going to be an induction effect which alters the outcome. Instead of me being able to just like instantly do whatever I want to the current, this Faraday's law and Lenz's law effect is going to hamper things. So here's a bunch of math to go with this. Again, the central idea is that the induction effect, I put the word tries in quotes here because obviously there's no like conscious entity involved. I shouldn't personify an abstract concept, but the induction effects will try to prevent whatever is happening, whatever change is occurring. Now, the induction effect is never strong enough to actually prevent things from changing, but it does slow them down or smooth them out, that sort of thing. So I'm going to make a definition here. This quantity in the red box, capital L, is called self-inductance, although in practice people usually just say inductance without the self. And it is the ratio of the amount of flux going through the coil to the amount of current that's going through the coil. So basically, the bigger the area is, or the more wrappings you've got for a given amount of current, the higher the inductance is going to be. So it's like a measurement of how much looping around is there, how much area, how much effective area do you have? And many books define it this way, the way I have it in the big box with this capital N. Some sources sort of fold the big N into the flux phi, and so they might define it as just phi over I instead. And this version, without the big N being explicit, seems to be the way the College Board does it. If you look at the way inductance formulas are written on the formula sheet, there's not a lot of big N's around, so this version, just phi over I. Seems to be the way the College Board does it. Big N is still important, it's just kind of like included. So you could think of the phi as being like the total amount of flux instead of just the flux through a single loop. It's already included all of the extra loops. The unit for this quantity has its own name. It's called the Henry, and the symbol for the Henry is a capital H. And the breakdown for the Henry is written here. The flux units is Tesla times meter squared, and then the current unit is the ampere, so it's Tesla meter squared per ampere. So that's our definition for inductance. But I want to relate this to Faraday's law, because that's the whole point here. So Faraday's law, the way we wrote it before, was like this. The EMF is negative n d phi dt. Again, you could include the n in the phi if you want to. That makes the equation look a little simpler than it's just negative d phi dt. But either way, n itself is a constant. And so when I take, so if I put that inside the derivative like this, I then notice that I have n times phi, but according to this definition of inductance, n times phi is the same thing as L times I. So that means that I can also write the EMF for Faraday's law as negative L di dt. L is constant, because L is just a property of like the device. So it doesn't have a time derivative. But I, the current, can have a time derivative if you're trying to change the current. So what this bottom equation here is saying is that if you have an inductor in your circuit, and again, an inductor is basically like any coil or loop of wire. If you have an inductor in your circuit, it will generate EMF in response to any change in the current level. The minus sign, again, is the Lenz's law part, and that tells you that the EMF it generates is going to be in the opposite direction from the current change. So if you try to increase the current, it's going to make a backwards EMF. If you try to decrease the current, it's going to make a forwards EMF. Always maintaining or trying to maintain the original current level. Now one thing I want to point out, I may have this written on a later slide, I forget, is that on the AP formula sheet, this definition for inductance is not there. They don't give you that formula. But they do give you multiple other formulas that have L in it, this being one of them, and actually this also. They do the version without the big N, but like they give you both of those, and so you can easily construct the definition of L from those two if you need it. Probably you're not going to need it. Okay, so again, the core idea that you need for inductors in a circuit is that they smooth out or slow down changes in current. And functionally speaking, in the very first instant, when you first make a change to the circuit, the inductor just maintains whatever the old current was, and then the current will gradually change or gradually approach whatever the final value is going to be. So, for example, if you are just first turning something on, suppose the circuit, everything was completely off and you turn it on, the inductor is going to push back against your battery. It's going to push back very strongly at first, and then its push is going to get weaker and weaker until it dies away. And so basically this means that it takes longer for the circuit to turn on. Instead of turning on instantly, it powers up over some short time interval. Similarly, if you try to turn off your circuit and it's got inductance, then in the first moment after you turn it off, the inductor is going to keep pulling current through at the same level as before, and then gradually the current will die out. So again, it takes longer for this to happen. Functionally, one of the things that we use inductors for as a practical matter is for filtering high-frequency noise or fluctuations in electrical signals. You have probably noticed little thicker parts around a lot of cables that you deal with in your everyday life. And those thick little plugs, those cylinders, that is just a bunch of wire all wrapped around. So like this wire is just wrapped around some sort of a core, and then it continues on afterwards. And the reason that it has that is to filter out these fluctuations that you don't necessarily want to get from one end of the wire to the other. Now, the inductor generates an EMF, right? That's the whole idea. The inductor generates an EMF. EMF is measured in volts. So if you take a voltmeter and you connect it to either side of an inductor, to either side of a coil, what you're going to measure, assuming that the coil has no resistance, assuming it's like an ideal inductor, it has no resistance, the potential difference that you get is going to be equal to that EMF, and so it has this magnitude L di dt. So any sort of circuit analysis that you're doing, if you know there's an inductor in the circuit and you want to write out like a Kirchhoff's loop rule, the expression that you would use for the potential difference for the inductor is the same as this EMF expression, L di dt. And I'll do a little bit with that in the next video. Okay, so I gave you a functional definition. L is n phi over I, or just phi over I. So let's talk about a specific object. Let's go with an ideal solenoid. The ideal solenoid formula is pretty easy. This is the magnetic field produced. It's in terms of your magnetic permeability mu naught, the density of the coils or turns, and the amount of current that's flowing through it. So for a given device, if you increase the current, the magnetic field gets stronger. And for a given current, if you have more wrappings, if the number density of the wrappings is higher, that also strengthens the field inside. And so you can write it in terms of either little n or big N. I'm noticing that that should be a big N, so I'm going to change that right now. Little n is the density of the turns, big N is the total number of turns. And this script L is the length of the coil. So our definition of inductance is this n phi over I. Phi, the flux, is the area of the coil, the cross-sectional area of the coil times the magnetic field. And I know that the magnetic field is based on the solenoid formula, because I'm doing it for a solenoid. And so if you consolidate your factors, simplify a little bit, you get these two expressions. One of them's in terms of big N and the other one in terms of little n. So that's specifically for an ideal solenoid. You can have other kinds of inductors, even just the circuit itself. If you just have an incredibly basic circuit that's just a battery and a resistor connected together into a circle, that is itself a loop. And so any circuit that you ever make is going to have some intrinsic inductance, even if you didn't deliberately put in like a solenoid or something like that. So these formulas are just for ideal solenoids. I have also assumed that there is nothing inside the coil, because this quantity, mu naught, that's the magnetic permeability of free space, which means it applies for vacuum. It basically also applies for air, just like that quantity epsilon naught that we had in previous chapters applies to vacuum or air. But if you have some sort of a substance, if you have matter there, then you would use the epsilon value for that substance. Same thing with magnetism. So in practice, solenoids often are wrapped around some sort of a cylindrical object to increase the potency of the magnetic field. Iron is a great choice. Iron is plentiful, and it has a mu value which is 5,000 times bigger than mu naught. So if there is a solid core, then you have to update your mu value. But if it's described as being an air core, then you can just use mu naught. And as I have in the note down at the bottom, I want to point out that although the magnetic field in a solenoid is proportional to N, the density of the turns, the inductance of a solenoid, the inductance L, is proportional to N squared instead. And that's because if you increase the number of turns, you're doing two different things. First of all, increasing the turns, for a fixed length at least, increasing the number of turns makes the magnetic field stronger, but it also means you have more loops of coil so that the total amount of flux is increased. So when you add more turns, you're strengthening the field and also increasing the effective area, and so you get this like extra strong effect on the inductance. Okay, so last thing for this video is I just want to make some comparisons with the other circuit elements that we studied this year. Resistance was defined as delta V over I, capacitance is defined as Q over C, and similarly inductance, I'm doing the version without the big N here. Inductance is the total flux over the current. So those are, again, the definitions for these quantities. They are based on the way the device functions, or the way it behaves. But then for each one of these devices, we have a secondary formula that comes from a particular idealized device design. So for a resistor, if you think of the resistor as being like this idealized cylindrical wire, you need to know about the resistivity of the substance, and you need to know its physical properties. How long is it? What's its cross-sectional area? For a capacitor, the idealized device is a parallel plate capacitor. So you need to know the dielectric constant for the stuff between the plates. That's again a material property that you would look up. You need to know the area of the plates and the distance between them. And then our idealized inductor is a solenoid. You need to know the permeability of the stuff inside it. You need to know how many turns there are. And you need to know, again, the cross-sectional area and the length. Now, it's very uncommon for the College Board to ask you to add series and parallel inductors, but if that comes up, you can figure out what the rules are the same way that you do for resistors and capacitors based on this row of formulas. For an inductor, the area is in the top and the length is in the bottom. So hold on a second, I am freaking out here. I have that. Did I write that backwards? I didn't. I don't know. I'm just going to cut out this part of the video because that was the end anyway.